Which illustration depicts a slightly low 2.8 degree indication? A. 10, B. 9, or C. 11? This is a question about Precision Approach Path Indicators, or PAPIs for short. They allow a pilot to judge whether or not he is making the correct angle of approach to the runway. They change color from white to red depending on whether he's too high, too low, or on the correct approach profile. Most PAPIs are calibrated to a 3-degree approach and will give guidance up to 0.5 degrees either side of this. The correct indication showing that we're on the 3-degree approach would be 2 whites and 2 reds, as shown here on the left side of runway 17 left at Orlando International Airport. So if 2 reds and 2 white lights mean that we are on the 3-degree glide path to the runway, and white lights mean that we're too high, and the PAPIs give us 0.5 degrees either side of the glide path for guidance, 4 white lights means that we are at or greater than a 3.5 degree approach to the runway, as can be seen here. As we start to correct, the lights gradually begin to turn red again. 3 white and 1 red would show approximately a 3.2 degree glide path towards the runway, as shown here. 2 whites and 2 reds mean that we're back on the correct 3-degree profile, as can be seen here. 3 reds and 1 white would mean that we're slightly low, which would mean that we're on approximately a 2.8 degree glide path towards the runway, whereas 4 red lights means that we're on or below a 2.5 degree path towards the runway. So we can see here then that we're slightly low on the correct approach profile, and the corrective action that must be taken is an increase in power and a pitch up, which will allow us to reduce our rate of descent while maintaining our speed. When we see 2 whites and 2 reds, then we reduce the power and lower the nose to maintain the speed to re-establish the correct 3-degree glide path. So the correct answer of which illustration depicts a slightly low 2.8 degree indication is C. 11. What is the correct sequence for recovery from the unusual attitude indicated? A. Level the wings, raise the nose to level flight attitude, and obtain the desired airspeed. B. Reduce power, level the wings, and bring the attitude to level flight. Or C. Reduce the power, increase back elevator pressure, and level the wings. So here's a situation that matches the figure that we're given in the question. We have an attitude indicator which indicates a low nose attitude and a bank to the right. We have a high indicated airspeed, a negative vertical speed, and an altimeter that's winding down, all supporting the low nose attitude indication. We have a right turn registered on the turn coordinator and numbers increasing on the direction indicator, all supporting the right bank indication. As all the instruments agree with each other, there's no reason to suspect that any of the instruments are faulty, and this would be how it would look outside the window if the weather was good. The airspeed is approaching structural limitations. We therefore have to prevent aircraft damage by preventing any further increase in the airspeed, by reducing the throttle to idle. Attempting to pitch the aircraft at this bank angle and airspeed would likely exceed loading limitations. We must therefore level the wings first. Once the wings are level, we can arrest the descent by pitching up to the level flight attitude. Once the airspeed has come back to a normal cruise airspeed, we can then reset cruise power and resume safe flight. So the answer to the question, what is the correct sequence for recovery from the unusual attitude indicated, is B. Reduce the power, level the wings, and bring the pitch attitude to level flight. On what headings will the magnetic compass read the most accurately during a level 360 degree turn with a bank of approximately 15 degrees? A. 090 degrees and 270 degrees. B. 135 degrees through 225 degrees, or C. 180 degrees and 0 degrees. This is a question about a compass turning error which is caused by a phenomenon called magnetic dip. This causes the compass to lag through north and lead through south. A major contributing factor to this error is the aircraft's latitude, as the Earth's lines of magnetic flux become more vertical with increasing latitude. We can therefore compensate for this error by using this general rule of thumb. Take half the latitude and plus 15 degrees. So in this case our latitude is 28 degrees, half of that is 14, and then plus 15 is 29 degrees, which we can call 30 as it's close enough. We can then apply the principle of undershoot north, overshoot south. So when approaching north, we need to roll out 30 degrees prior to the compass reading north. When approaching south, we need to roll out 30 degrees after the compass has passed through south in the northern hemisphere. Unfortunately, the simulator doesn't quite show the number of degrees of compass error that we would experience in real life, but the principle is generally shown. This error is at its maximum on the north and south headings, and the error is non-existent on east-west headings. And the error reduces linearly between the polar headings and the east-west headings. So the answer to the question on what headings will the magnetic compass read the most accurately during a level 360 degree turn with a bank of approximately 15 degrees is A, 090 and 270. Which distance is displayed by the DME indicator? A, line of sight direct distance from the aircraft to the vortex in statute miles. B, slant range distance in statute miles. Or C, slant range distance in nautical miles. I currently have the aircraft set up inbound to the Treasure vortex, which is on a VHF frequency of 117.3. As far as civilians are concerned, this is a VOR with the DME co-located. DME operates in the ultra high frequency band. However, it's always co-located and tied to a VHF frequency, so it never needs to be tuned separately. The DME acronym stands for the imaginative name of distance measuring equipment. It couldn't have taken long to come up with that one. You'll see here at the bottom of the PFD, I have a DME readout set up. You'll also see at the top of the PFD here, there's another distance readout, which is a GPS readout which I've set up for comparison purposes. Both readouts are given in nautical miles but are taken from different sources. DME works on a principle of interrogate and response, so sends a message to the DME station and then receives a reply, and then calculates the distance from the station based on the time taken to receive the reply. Given the way this is calculated, this will always be an exact distance between the aircraft and the DME station. If we were to think of this as a right-angled triangle, we are therefore measuring the hypotenuse, which is the longest side of the triangle, and will therefore give a figure which is a higher value than the actual distance over the ground to the station. This is called slant range. So as we get closer to the DME station, notice how the GPS distance reduces at a faster rate than the DME readout. This is because the triangle that we were talking about is becoming more squashed, and therefore the hypotenuse is much longer than the ground distance vector. This error becomes more and more apparent the closer you are to the station, and the error is at its maximum when we are directly over the top of the DME station. At this point, the DME is reading the height above the station in nautical miles. Now in this case, the station is at sea level, and we're at 3,000 feet altitude. You'll see as we come over the top of the DME station that the GPS readout is almost reading 0, whereas the DME is still telling us that we're half a mile from the station. That's because there are approximately 6,000 feet in a nautical mile, and therefore we are about half a mile above the station. Here's an example of crossing the DME station at 6,000 feet. Notice the greater difference between the DME readout and the GPS readout than the difference was reading at 3,000 feet. You'll also notice that as we cross the DME station, the GPS readout will reach almost 0, whereas the DME readout will not read less than 1 nautical mile. And that's because, as stated before, there's 6,000 feet in a nautical mile, and we're therefore 1 nautical mile above the station. And finally, here we are crossing the DME station at 12,000 feet, which took me about 12 years to climb to in the Cessna 172. See, the distance on the GPS is 1.1 nautical miles, and the distance readout on the DME station is 2.2 nautical miles. Therefore, that's quite a large difference. As we cross over the DME station, you'll see that the DME readout does not read less than 2 nautical miles. And once again, that's because there's 6,000 feet in a nautical mile. We're therefore 2 nautical miles above the DME station at this point. So the answer to the question which distance is displayed by the DME indicator is C, slant range distance in nautical miles. On the basis of this information, the magnetic bearing to the station would be 355, 255 or 175. Now the information that it's referring to is this figure, which shows heading information and a relative bearing indicator. These show a heading of 215 and a relative bearing of 140. So what I've done here is set the sim up on a heading of 215 on a relative bearing of 140 with respect to the Golf November NDB here. You can see that places the NDB behind us and to our right. This exactly duplicates the figure that you saw in the question earlier. The most accurate way of calculating the magnetic bearing to the station is to take the magnetic heading and add it to the relative bearing. So in this case, 215 plus 140, which will give you 355 degrees. In a more practical sense, some pilots find it easier to look at the relative bearing indicator and transcribe that across to the heading indicator. The head of the needle points to the bearing to take to the station, which you can see is 355 in agreement with our calculation. Now all that's left to do is to make the turn towards the NDB. As the turn progresses, you will see the relative bearing change as the nose starts to point towards the NDB. In a zero-wind situation, the relative bearing indicator will point directly upwards when established on the track to the NDB with the wings level, as you can see here. And that's it, we're now established inbound to the station. If there was any crosswind component, it would be important to make a correction to the heading to maintain the correct track. And that's how to answer the theory question and how to deal with it practically.